Imagine a world where a single tiny particle, so small that it cannot be seen with the naked eye, holds the key to understanding everything around us. This world is not a fantasy. It is the world of atoms. On August 6, 1945, when the atomic bomb was dropped on Hiroshima, the world was introduced to the dark and powerful secrets of the atom. But the journey to this moment began long before, with ancient philosophers and curious scientists who dared to think about the smallest units of matter. The story of the atom starts with a legendary Greek philosopher named Leucippus, who lived around the 5th century B.C. His student, Democritus, known as the laughing philosopher, developed the idea further. Democritus believed that everything in the universe was made up of tiny, indivisible particles called atoms and empty space, or void. These atoms, he argued, were eternal and indestructible, and they combined in different ways to form everything we see and touch. Democritus's ideas were revolutionary because they challenged the dominant belief in a world controlled by gods and supernatural forces. He suggested that the universe was governed by natural laws, and that understanding these laws could help us make sense of the world. This philosophy of atomism was a seed that would grow and influence science for centuries to come. During the Middle Ages, atomism was largely forgotten or suppressed by the Church, which preferred explanations based on divine intervention. However, in the Renaissance, ancient texts were rediscovered and studied. One of these texts was the Latin poem De Rerum Natura by Lucretius, written around 55 B.C. Lucretius's poem was a passionate defense of atomism, aimed at freeing people from the fear of the gods and the afterlife. He argued that the soul dies with the body, and that the fear of death was irrational. Understanding nature, he believed, was the key to peace of mind. Lucretius's ideas were a breath of fresh air in the Renaissance, and they influenced many great thinkers. One of them was the English philosopher Francis Bacon, who saw the potential of atomism in explaining natural phenomena. Bacon's interest in atoms laid the groundwork for the scientific revolution that followed. The scientific revolution brought a new way of thinking about the world, based on observation and experimentation. One of the key figures in this revolution was the French philosopher René Descartes. Descartes proposed that the universe was made up of infinitely small particles, moving through a medium he called the ether. Although his ideas were different from those of the ancient atomists, they contributed to the growing interest in the nature of matter. Another important figure was the French philosopher Pierre Gassendi, who revived and modified Democritus's ideas. Gassendi's version of atomism influenced the English chemist Robert Boyle, who used it to challenge the traditional belief in the four elements: earth, air, fire, and water. Boyle's experiments showed that these elements were not indivisible, and that matter could be broken down into smaller components. The person who truly brought the atom into the laboratory was John Dalton, a self-taught Quaker from a family of weavers in the English Lake District. Dalton's interest in science began early, and he was influenced by a blind natural philosopher named John Gough, who taught him mathematics, astronomy, and observational science. Dalton's curiosity led him to study the atmosphere, which eventually brought him to the world of atoms. Dalton's breakthrough came when he realized that different elements combined in fixed ratios to form compounds. This idea, known as the law of definite proportions, suggested that elements were made up of small, indivisible particles atoms. Dalton's atomic theory provided a framework for understanding chemical reactions and the behavior of matter. He proposed that each element had its own unique type of atom, and that these atoms combined in specific ways to form molecules. Dalton's work was a turning point in the history of chemistry. It provided a clear, logical explanation for the behavior of matter, and laid the foundation for modern chemistry. His ideas were later expanded and refined by other scientists, but the core principles of atomic theory remained the same. In the late 19th and early 20th centuries, the study of atoms entered a new phase with the development of quantum mechanics. Scientists like J. Thomson, Ernest Rutherford, and Niels Bohr began to explore the inner structure of the atom. Thomson discovered the electron, a negatively charged particle within the atom. Rutherford's famous gold foil experiment revealed that the atom had a dense, positively charged nucleus, surrounded by a cloud of electrons. The work of these scientists led to the development of the quantum model of the atom, which described the behavior of electrons in terms of probability. This model explained why atoms have specific properties and how they interact with each other. The quantum model also had far-reaching implications for our understanding of the universe, from the behavior of stars to the structure of materials. The discovery of the atom and the development of atomic theory have had a profound impact on society. The most dramatic example of this impact was the development of the atomic bomb, which demonstrated the incredible power of atomic energy. The atomic bomb not only changed the course of World War II, but also raised profound ethical and moral questions about the use of such destructive technology. In the years following World War II, atomic energy was harnessed for peaceful purposes, such as generating electricity and advancing medical treatments. Nuclear power plants provide a significant portion of the world's electricity, and radiation therapy is used to treat cancer. However, the use of atomic energy also comes with risks, such as the potential for nuclear accidents and the problem of radioactive waste. The study of atoms continues to be a vibrant field of research. Scientists are exploring new ways to manipulate and control atoms, from nanotechnology to quantum computing. These technologies have the potential to revolutionize fields such as medicine, materials science, and information technology. Nanotechnology, for example, involves the manipulation of matter at the atomic and molecular level. This technology has the potential to create materials with unique properties, such as stronger, lighter, and more durable materials. Quantum computing, on the other hand, aims to build computers that use the principles of quantum mechanics to perform calculations that are beyond the capabilities of classical computers. From the ancient philosophers who first imagined the atom to the modern scientists who continue to explore its mysteries, the story of the atom is a testament to human curiosity and ingenuity. The atom has shaped our understanding of the world and our place in it, from the structure of matter to the behavior of the universe. As we continue to uncover the secrets of the atom, we are reminded of the power of human thought and the importance of scientific inquiry. The journey of the atom is far from over, and its future holds the promise of new discoveries and innovations that will shape the world in ways we can only imagine.